Okay, in this session, we'll learn about the moment distribution method. Now, moment distribution method is an extremely powerful method, and it's very ingenious also. So, and let's see a little bit of review of what we did earlier when we were considering the displacement-based methods. Okay, so the basic idea was that we were fixing both ends A and B. Okay, and then by uh, sequentially releasing the joints which were to be released, and by assigning subsequent moments for those unknown rotations, we were able to calculate these rotations and subsequently the moments when we were doing the slope deflection method. Okay, so for example, in this situation where both ends are fixed, I mean the far end was fixed, the moment required to induce this unknown rotation theta a, right? This was 4 ei by L times theta a. Okay, and because of this unknown moment, because of this moment when it was applied, there was an induced moment at B, which was 2 ei by L times theta a. Okay, and these form the basic equations of the slope deflection. And once we were solving that, we were able to find out theta a, theta b, and so on, right? So this was one of the things. Then we had one more situation where the far end was, let's say, pinned. So in this case, the end B is a pinned support. Okay, in this case, the moment required to induce this unknown rotation of theta a, that we calculated to be 3 ei by L times theta a. Okay, so we use this for the moment balance at a joint, and subsequently we were able to solve for these unknown rotations. And once we found the rotations, we were able to find the moments, right? And after moments, we were able to do force balance to find all the forces, right? Similarly, there was one more situation where the far end was a guided fixed support, and this happened primarily when there were uh, there was a structure with symmetries, and in this case the moment here was just ei by L times theta a. Okay, and the moment induced on the other end was minus of the same one, so minus ei by L times theta a. Okay, and of course in the far end pinned case there was no moment which was induced on the end B. Okay, so that was 0. Okay, and so let me try to just again reiterate what we did in slope deflection. So let's say we had a structure which is shown here, ABC, right? And it has some applied loads, these loads being shown in green color. Okay. So what we did first was we made a primary structure, right? So primary structure was made by fixing B and C, in fact by fixing all the joints which were there, right? And with respect to this primary structure, we calculated the fixed end moments. Right? Fixed end moments were coming from the applied loads. Okay, so this was one set of moments which were induced, and these were a result basically of fixing the joints which were not fixed. Okay, and application of the external loads. Then we released one of these joints, right? So we said that the total rotation at theta at B has to be theta B, and that theta B is not known. Okay, we said let's induce an unknown rotation theta B at B while we retain the other ends fixed. Okay, and to induce this theta B, there will be the moments which we just shown above, that 4 ei by L theta B, right? So and then for the span AB, the moment induced at A will be 2 ei by L theta B, and for BC it will be 4 times. So that is how these moments are induced, right? And once we allowed B to rotate, then we went to the next joint C. We said now we allow C to rotate by an unknown amount of theta C. Okay, so and once both of these we allowed to rotate, we wrote two in this case equilibrium conditions, right? So MB equal to 0 and MC equal to 0. Total moment at each joint should be 0 because eventually they are the roller supports or pin supports, so there should be no moment in a net sense. And these two equations we were able to write in terms of something like that, where the unknowns theta B and theta C were there. This was the matrix which we said will be the the stiffness matrix in a sense, right? And this right hand side vector was coming from the fixed end moments. Essentially, the negative of the fixed end moments was this right hand side vector, right? And by solving this, we were able to find out theta b and theta c, and then we put them back into the slope deflection equation. We were able to find all the moments, right? So that the approach we took, that was a direct solution, right? So when we say direct solution, what it means is that this system of equations, the linear system of equations in theta b and theta c, we were solving directly by inverting the matrix, right? Or in linear algebra, you might have heard about, let's say, LU decomposition. So that is a direct solution approach. So that kind of approach we were using to solve, right? Similarly, there was a situation where we can shorten the procedure by considering that if the far end C is pinned, right? So we do not fix it in the primary structure to start with. Okay, so we fix only the joint B, which is in the middle, and then we allow it to rotate by theta B. We do nothing to the joint C, right? We allow it to rotate naturally, and then we end up having one equilibrium condition, which is MB equal to 0, and in this case MC equal to 0 is automatically fulfilled. And again, that leads us to one equation from where we can solve for theta B, right? And again, we were using a direct solution scheme where we were able to solve this for theta B, and once we solved for theta B, we were able to calculate the other moments. Okay, now the moment distribution method basically allows us some sort of an iterative solution. Okay, so one of the drawbacks, if I may call it, for the slope deflection method will be that if the system is very large, right, which means if this matrix which is to be inverted is very large, it becomes very difficult to invert that by hand. I mean, we will need to use a computer program to invert it. Okay, if this matrix is large, let's say 5 more than 3 by 3, so up to 3 by 3, I think it is relatively easy to invert it by hand, but more than that, it will be a problem. Okay, so this is where this direct solution computation by hand becomes a problem when we are dealing with large problems, okay, large systems. So this is where moment distribution method is extremely useful, and it was developed by someone by the name of Hardy Cross. And if you have taken a course in pipe networks in fluid mechanics, you would have also come across a similar type of iterative scheme for solving pipe flow problems. Okay, so the same idea is used here in trying to find an iterative solution of this system, right? So the system of equations we are solving is the same as what we were solving in the slope deflection equations. Okay, however, the solution procedure is different. Okay, so just to give a brief idea about this difference between direct and iterative, let's say this is a system that we wanted to solve. Okay, this is a hypothetical system, but let's say this is what we wanted to solve. So if we do a direct solution, we will invert this matrix, and we get this type of solution, which is a direct solution. Okay, now an iterative scheme is possible. Okay, so when we were saying direct solution, we were using something like an LU decomposition type of approach. Now, if we want to think of an iterative solution, so iterative solutions usually start with an initial guess, right? So let's say we choose an initial guess for theta c. Let's say theta c, we start at 1. So this is an initial guess which we will keep updating with time. Okay, now there are 4 relations which we have. So basically there are 2 relations, but we can repose it in 2 different forms. So these 1 and 2, these are the moment balance equations for, let's say, 2 joints which are available. So these are direct consequence of the matrix equation that we have, right? So this one of them, let's say we rewrite in terms of theta b. Okay, we call it A, and one of them we rewrite in terms of theta c, and we call it B. Okay, so what it means is that if we know theta c, we can use this A to calculate theta b, and if we know theta b, we can use this B to calculate theta c. Okay, so we start with an initial guess of theta c. Okay, so we start and when we satisfy the equation A, what we are saying is that moment at B is getting balanced. Okay, so that is so this equation A is originating from 1, which is moment balance at B. Okay, so we start at, let's say, theta c equal to 0. We put it here in A. Okay, so we get some value for theta B. Okay, so if theta 1 was if theta c was equal to 1, we will get theta b equal to 7, and this will satisfy the moment equilibrium condition at B. But if we check moment at C, which is from the second equation, we see that it comes out to be -2, which means that now joint C is unbalanced. Okay, so now let us use further try to do this at iterative process. We say that now we use equation B to set moment at C equal to 0. Okay, and now whatever theta b we found earlier, right, that we put here in the moment at C equal to 0 balance equation, right? So from here we will get some number for theta c. Let's say we get 1.5 in this case. Okay, so at this point, what it means is that now MC is balanced, because MC equal to 0 has been satisfied for theta b equal to 7. But now we'll have to check for MB, right? So we take this updated value of 1.5, right, and the value of 7 for theta c and theta b. Okay, now we see that MB is not 0, it becomes 1, right? So now MB is unbalanced. So then again we continue the iteration process. Next we again go back to A and we say MB equal to 0, and this 1.5 value of theta c we put there to find theta b. Okay, and we come with theta b value to be 6.8, and now MC becomes unbalanced, right? Then we again go back to the MC equation. We put this 6.8 there. We find a new value for theta c. Now MB becomes unbalanced, right? So what we can notice here are a few things. One is that the amount of imbalance is reducing with the increase in number of iterations, right? So first, in the first iteration, MC was unbalanced by -2, right? And in this, MC is now imbalanced by -0.4. So the amount of imbalance has reduced. So this eventually we would want to reach 0. Okay, so both of these imbalances, they have to reach 0 for this iteration to have converged to a final solution. Okay, another thing which we can notice is that, let's say we started with theta c equal to 1, then theta c became 1.5, then 1.6, and if you look the earlier exact calculated values of theta b and theta c, they were 6.67 and 1.67. So that is visible in the inset that you see there. So what we see is that from 1 to 1.5 to 1.6, so theta c is actually tending to the actual value of 1.67, and similarly the first value of theta b which was calculated was 7, right? Then it went to 6.8, and what we see is that this theta b equal to 6.8, this is also tending towards the exact value of 6.67, which is what we calculated earlier. Okay, so in this manner, what we see is that this iteration scheme is actually converging towards the exact solution, and this type of iteration scheme from a linear algebra perspective is very close to the Gauss-Seidel method. Okay, so this Gauss-Seidel method gives us a way to iteratively find solutions of linear system of equations. And similarly, the moment distribution method allows us to iteratively solve the equilibrium equations of joints, which we generated using slope deflection method. Okay, so now one thing on the side of moment distribution is that since there is no need to explicitly invert a matrix, regardless of the size of the system, we will be able to use this method very effectively. Okay, so basically this is an iterative joint equilibrium satisfaction method. Another thing we will see in this is that the thetas or the unknowns will not be directly calculated. Okay, so by using moment distribution method, we will end up getting directly the end moments. We will not really calculate the thetas while we solve the systems. Okay. Okay, now before we start discussion on moment distribution method, just a few other small points. So one is the terminology of stiffness coefficient and a carryover factor. Okay. So these figures we have seen earlier. This is far end fixed, far end pinned, and far end on a guided fixed support. Okay. Now to induce a value of 1 unit rotation at joint A, right? So now we are just setting all the thetas to 1. That will mean that whatever moments we required can now be called stiffness coefficients, right? So the stiffness coefficient in this case at joint A is the moment required to produce a rotation of 1 at joint A, right? And that is 4 EI by L. And once we apply 4 EI by L at A, at joint B, there is an induced moment of 2 EI by L. Okay. So it's like that we apply this moment, and this moment is getting carried over. Okay. It is getting carried over to the other joint by a factor of half. Okay. So if we apply M here, M by 2 is getting transferred to the other joint with the same sense. Okay. Similarly, if we are dealing with a far end pinned, the induced or the required moment or the stiffness coefficient is 3 EI by L, but the carryover factor in this case is 0 because there is no moment which is going to the far end. And similarly for the guided fixed support, the stiffness coefficient is EI by L and the carryover factor is -1. Okay, because when it is going to the other side, it goes with the opposite sign. Okay, so this is a brief table which summarizes this discussion, and these will be extremely useful when we go on to discuss moment distribution method. Now there is one more interesting thing which we can discuss before we actually go on solving problems with the moment distribution is the view of the beams as a flexural spring. Okay, so I'm sure all of you would have looked at a picture like that, right? So where there is a spring, you hold that spring and you pull on one end with a force. Okay, so if you pull on that with a force of M, okay, and the spring constant, let's say, is K, then that force, and if theta is the displacement, the linear displacement along the direction of the force, then the force is equal to K theta. This is the basic linear spring relation, right, where F equal to Kx or M equal to K theta in this case. Now consider what is happening here in the beam. Okay, let's say if let's say this end, if let's say it is A. Okay, and at A we are allowing or we are causing a rotation theta A, or in a way a displacement theta A, right? And for causing that displacement, we need to induce or we need to exert a moment of 4 EI by L times theta A. Okay. Now this is actually it is actually same as that of spring, right? Just that this 4 EI by L, which we were calling stiffness coefficients, or which are the stiffness coefficients, right? This is like the spring constant, right? This theta is like the displacement, and this M is like the force, right? So this beam is acting like a flexural spring. So for rotation, there is a force needed, and for that force and the rotation, there is a relation through the stiffness coefficient, which is 4 EI by L in this case. Okay, so there is a one-to-one relation, or there is a one-to-one correspondence between a linear spring and a rotational spring of a beam, or a flexural spring of a beam, which is what we are seeing here. Okay, now let's dwell on one more thought. Let's say there are two springs which are applied in parallel. So they are fixed on one side to a wall, and on the other side they are being fixed to a, let's say, a rigid bar which is being pulled with a force F. Okay, and when we pull on them with the force F, both the springs experience a displacement delta on one side. Okay, and in this case, let's assume that the springs have different constants K1 and K2. So the spring constants are different. Okay, now we may consider the first spring. Okay, so first spring has a displacement delta, and we can find out what force was required to induce that displacement delta. So that will be, let's say, F1, which is K1 times delta, right? Similarly, for the second spring, we can find out what was the force needed to induce delta in just the second spring, right? So that will be F2 equals to K2 times delta, right? And then we can do the force balance of the rigid arm which was connecting both of them. So from there we will get F equal to F1 plus F2, which is equal to K1 plus K2 times delta. Okay. So here there is a concept of distribution which comes, right? So this will be the distribution part of the moment when we talk about moment distribution, right? So in these springs, we can ask a question: what is the proportion of the force F which is distributed to spring 1? Okay, or what is the proportion of the force F which is carried by spring 1? Okay, so that will be, the proportion will be F1 by F, right? So force in spring 1 divided by the total force. So that comes out to K1 divided by K1 plus K2. Okay, similarly we can ask what is the proportion of F which is distributed or which is carried by spring 2, right? So that will be F2 by F, and that comes out to K2 divided by K1 plus K2. Okay, and these factors, these are called distribution factors, right? So this is dF1, which is distribution factor for spring 1, and this one is dF2, or the distribution factor of spring 2. Okay, and for obvious reasons it is easy to check that the summation of the distribution factors of springs connected to a single point, that will be 1. Okay, now let's carry this further to the discussion on beams. Okay, so let's say there is a frame which is given like this, A, B and C, and let's say at joint B there is a moment m bar which is being applied. Okay, now the member AB has a far end which is pinned, so the stiffness coefficient here will be 3 EI by L, so KAB will be 3 EI by L, and member BC has a far end which is fixed, so KBC will be 4 EI by L, right? So if we calculate the distribution factor of BA, right, so at joint B there is a total moment m bar being applied, so there will be some moment which will be kept taken by MBA, which is towards the A side, and there will be some moment which will be taken by the BC arm. Okay, so one of them we are calling MBA and one of them we are calling MBC. So for us to be able to calculate that, we need the distribution factors at BA and BC. So this is simply 3 EI by L, which is the stiffness factor of BA divided by the total stiffness of that joint, right? So that is K1 plus K2. So distribution factor of BA comes out to 3 by 7 and that of BC comes out to 4 by 7, right? So then we can calculate the proportion of moment of m bar in AB and proportion of moment of m bar in BC, which is basically coming directly from the distribution factors. Okay, so this image shows just that. So whatever moment was applied at B, right, so 3 by 7 of that that is now carried by member AB, and MAB, which is moment here, will be 0 because the carryover factor is 0, right? So the far end is pinned, we used 3 EIABL as the stiffness factor, so the carryover factor in this case is 0. Okay, now for the member BC we were using 4 EIABL, far end was fixed, and the carryover factor is half, so whatever M is induced at BC end, MCB will be half of that. Okay, so this is how the distribution and the carryover will take place.